January.
To start, what I'd like you to do, make a graph of time in seconds. All right, and then this is height in feet. And what I'd like you to do is graph the following function, f of x is equal to negative 16x squared plus 100.
What do you call it?
Yeah, but you need to make it like this. It needs to be big, that there's graph paper over here. In order to graph this, it would probably benefit you to have something to write on and something to write with other than your finger and your desk. I realize when you hit hard enough, you probably get your finger to work right with, but I'd rather if you use a pencil and paper. Probably work better.
Oh, my gosh. No.
It broke. You know, creative.
So how many seconds do we have to go to?
3.
3?
Yeah.
Okay. And how many height, how far do we go?
You'll see. Go ahead and put it in 0 seconds and see what happens. This is the function for a falling body falling from 100 feet. This is the function because negative 16 feet per second squared is the effective gravity. Calculus, you're going to learn a new concept today. Has to do with instantaneous velocity. Some of you may have heard of it from physics, I don't know. And we're going to learn about instantaneous velocity and a few other things. You need to graph this first. Go ahead and get your graph going. You've already graphed it.
Can we go by pen?
Sure, it doesn't matter.
Yeah.
I'm not even gonna put a scale on there. I'm just gonna put my points. I'm just gonna put 100 and get everything else from there. I'm just gonna put 100 up here. I'm not gonna worry about the scale. Yeah. Definitely not gonna go any higher. Fall off the cliff and hit the ground. I had a video to go with this, and you got to see the guy fall off the cliff, and then they plotted it and everything. But unfortunately, I put it in my second VCR, so I wanted to copy the first part of it, and my VCR decided to eat the tape. So I'm going to take it apart and see if I can save the tape. I haven't had a chance yet. So I'm going to do it myself. All right. We started at 0, what?
0, 100.
0, 100 is your first point. At 1 second, we are what height? 84. At 2 seconds, we are at 80. So substitute 2 squared is 4 times negative 16 is negative 64 plus 100 is
30.
36. That's good.
What did you say on the bottom say?
Time in seconds.
Oh.
This is time in seconds. This is height in feet. This is 2. What is it?
36.
You'll notice that this is not a straight line. It starts out slow, and you tend to fall faster and faster and faster as you fall down. We're probably going to hit somewhere between 2 and 3 seconds. In fact, we can be almost sure of it because it's going faster and faster every time. What I'm interested in right now is I'd like you to find the slope of the line between the first 2 points. So I'd like you to find the slope of this line right here. And the slope between the first 2 points. Go ahead. How do we find the slope between the 2 points? y2 minus y1 over minus. Do not copy what I write. I can get second graders to do that. All they have to do is write down what numbers they see in letters. That's okay, but that's not going to teach anything. You want to work ahead of me. The slope is negative 16 over 1. Negative 16 dogs? Negative 16. I'm sorry, there's no dogs in this problem. Speed per 1 second. This is a rate of change. Over the first second, he fell 16 feet. That means that his average rate of fall was 16 feet in the first second. But he started at 0. This part, 0, right? He's not falling at all. And then all of a sudden he falls off, and over the first second he falls 16 feet. That means that his average rate of speed was 16 feet per second. Do the next two.
How do you get the points like 184?
Substitute them into the function. This function represents a falling body from 100 feet. Now find the slope between the next 2 points. Notice that it's steeper. Parabolas do that. They get steeper as we go along. Its rate of fall increases. Find the slope. For me. His speed between 1 and 2 seconds was 36 minus 84 over 2 minus 1, which is negative 48 over 1, which is negative 48 feet per second. That's his average speed over between 1 and 2 seconds. But notice that his speed is constantly changing. In other words, he's constantly increasing. He keeps falling faster and faster and faster. Starts out slow and goes faster as he goes down. He keeps speeding up. What we're really interested in is instantaneous velocity. We want to know at, for example, maybe a half a second. It's somewhere in the middle here, isn't it? Maybe we want to know exactly how fast he's falling at a half a second, at one particular point in time. But we have a problem. You can't find the slope through one point, can you? You guys remember what we call this in geometry when you talk about a line that touches a curve at one point? It's called a tangent line. It touches the curve at exactly one point. It exists, doesn't it? And it must have some kind of a slope. Notice that the slope is changing. It's getting steeper. Anybody see that it's getting steeper as it goes down? But what I'd like to do is be able to find the slope at any given point. Notice that it starts out kind of slow, and then he kind of speeds up as he goes along. What we want to find is instantaneous velocity, which is the slope of this line at any given point. Well, fortunately for us, Isaac Newton figured out a trick for this. He found a way to get the instantaneous velocity at a single point. And he used a trick. Here's what he did. He took this curve, and he said, same curve, apples falling off the tree. It's like this, right? And he said, well, it takes a certain amount of time, but somewhere on this curve, there's going to be an x point that I might be interested in. And of course, this point is x, f of x, isn't it?
Yeah.
You clear? That's what x, y? I have a point. Now what I'm going to do, he wants to find the slope of the tangent line. He wants to find the exact rate of speed that this thing is falling at this point. So he thought of a trick. This is a really cool trick. He actually came up with this on his own, which is a really difficult concept. What he said is, what if I get really close to x? What if I pick a number that's really, really close to x? Does this sound familiar?
Yes.
Really, really close to x. He's going to pick a number that's so close to x, in fact, that you can't even express it as a decimal. It's so close. It's going to be x plus a little tiny number h. In other words, he's going to just add a little tiny bit to x. It's actually obviously not that big, right? Does everybody see that I get a different point that way? And what is my point then up here? It's that x plus h and f of x plus h.
Okay, why would you want to do that?
Because he wants to find instantaneous velocity. He wants to be able to figure out how fast is an object falling at any given time. Now he can figure out the average speed if he has two different times, right, for the first second, and he can figure out the average speed for the second couple of seconds. But it's important to find this, and I'm going to show you an application of this after a little bit. But assume that you want to find it. This is the way he decided to do it. Now it seems like he could have just, couldn't he have picked just like a number, like 2, and then a number maybe 2.1? Doesn't that sound reasonable? And they're so close together that maybe it doesn't matter. But what he found was 2 points that are actually in the same place. And they are different points, aren't they? Here's how he did it. You see, h is a tiny number. Write a very, very small number for h. Let h equal a very small number. Tell me what's a very small number. There you go. That's what h is equal to. The incredible thing is that h has this value, but it just happens to be exactly equal to 0.
If it's a small number, why is it exactly equal to 0?
I'll show you. I'm just going to prove it for you, okay? Take 1/3, and what's it equal to, everybody? Yeah? All right. Are these exactly equal?
Yes.
Is this exactly equal?
Yeah.
Now, multiply this side by 3, and we get... How far is this away from 1?
Very, very close.
Isn't it exactly that far away from 1?
Oh.
But it's not exactly 1.
Let's see. According to algebra, can I multiply by 3 on this side? Can I multiply by 3 on this side? And they better stay equal, right? What's 1/3 times 3? 1. They're exactly equal. Now, this is the idea behind calculus. It's a very difficult idea. That if you get small enough, it ends up being exactly equal to 0. You actually get to a limit. But don't worry, I'm not going to get into the specifics of this. I just want to show you where it comes from. What we're going to do is we're going to shortcut all that. We're going to use calculus. Now, he came up with this idea using this. And they explain it in your book, too. The idea is that if I find the slope through these 2 points, they really represent 1 point, don't they? You understand that x plus h is exactly equal to x? But mathematically, they're 2 separate points, aren't they? And I can actually find the slope through those 2 points, which really is 1. It's a little bit difficult conceptually. Like I told you before, the good news, calculus is very, very easy to do. It's very, very difficult to understand. Now we're going to do some calculus, and it's very, very easy. We're going to use a thing called derivative. And I'm going to give you another function, a nice easy function to do it with. What I'd like you to do is graph f of x equals x squared. Everybody graph it. That's a square. There we go. And what we're going to do is we're going to do a little bit of calculus. We are going to find the derivative of this function.
What's the derivative?
Absolutely fine. The way we find the derivative originally, and the way that Newton did it, was he actually took x and x plus h, f of x and f of x plus h, and actually found the slope between the 2 points. We're going to find the derivative with the shortcut that he found.
What is
The shortcut for derivative is take the exponent, multiply it by the coefficient, and then subtract 1 from the exponent. To find the derivative of a function, in this case, there's other kinds of derivatives, but we're going to deal with real easy polynomial derivatives. We always do it the same way. We take the exponent of the function. What's the exponent? 2. We take the exponent, 2. We multiply it times the coefficient. What's the coefficient?
1?
1. We take the 2 and we multiply it times the 1 and we get
2.
2. We write that down. F prime of x, which is the derivative. 2 times 1 is 2. Then we take the exponent and we subtract 1 from it.
1.
X to the 1. There. We took the derivative. Like I said, calculus is very, very easy to do. You always do it the same way. You take the derivative. This is half the calculus, guys. You take the derivative, you multiply the exponent times the coefficient, and you subtract 1 from the exponent. I know it's really tough to do, but that's what you got to do. Now, this is a derivative. Now, what the derivative tells us or gives us is the important part. What the derivative tells us is the rate of change or slope at any point. I can choose any point on this graph, and I can find the slope at any point. Look, I'm going to find the slope at this point right here. You understand what I mean by the slope at that point? It's a tangent line. Look, you understand that my tangent line is increasing as it comes up? Look, you see it?
Mm-hmm.
My tangent line is getting steeper and steeper as it goes up. I want to find the slope at 1, which happens to look something like this, doesn't it? Got it? Everybody understand that that's the tangent line that touches that curve in one point? I want to find the slope. The slope is right there, 2x. Let's see. What's the point that I just pointed out here? 1, 1. What is the slope at that point of the tangent line? 2 times x. What's x?
1.
So what's the slope at that point?
2.
2. The slope of this line. See the green line here? See this green tangent line right there? Its slope is 2x because x times 2 gives me 2, m equals 2. Find the slope at this point right here, at the red point. What is the red point?
2, 4.
2, 4. And the slope of the tangent line at the red point is
4.
4, because it's 2 times x. Whatever x is, you multiply it by 2, and you get the slope of the tangent line at that point. There's my tangent line, and it has a slope of
4.
4, because 2 times 2 gives you 4. So why do we even have that one? Why do it? For the first? Well, it doesn't have to be there, does it? You can write it or not, it doesn't matter. It's still there, even if you take it away, right? So then it's still 2x to the first?
Yeah.
Doesn't matter. All right, what's this point up here? Third one up here, the black one.
3, 9.
3, 9. And what is the slope of the tangent line at that point? M equals 6. If I draw the tangent line, it's going to have a slope of 6. It touches the curve at exactly 1 point. Now what I'm going to have you do is find the equation of the tangent line in each case. I'd like you to find the equation of the line that goes through 1, 1 and has a slope of 2. How do I know the slope at these points, guys? The slope is equal to the derivative at any point. 2x. What's x? What's the slope? 2. 4 and 6. By the way, folks, what would the slope of the tangent line be at here? Negative 2 and negative 6. It would actually look like that. Got it? All right. Find the equation of the tangent lines. This first one has a slope of 2, and it goes through the point 1, 1. What I'd like you to do first is go ahead and use y equals mx plus b, and then I'm going to show you the other way to do it. You're going to want to do it the other way, and I'll show you the difference. There's 2 ways to find the equation. I taught you y equals mx plus b because it's very applicable to word problems in linear algebra. We're going to learn a little bit more formal way of finding it, and I think you'll understand it real well that way. Let's start with the y equals mx plus b.
Y equals 2x minus 1.
Yeah. We substitute in for y. What is it? 1. M? X? 1 plus b. And we get 1 equals 2 plus b. And we have to subtract 2. And we get b equals negative 1. So our equation is y equals 2x minus 1. This is the equation of our green tangent line. What we're going to do from now on, though, is we're always going to use the point-slope form unless we're doing word problems. You're going to like it a lot better. Because what I want you to do is I want you to think back to how you figured out where the center was on an ellipse. How do you find the center on an ellipse, a parabola, a hyperbola? How do you get the center? X minus something and y minus something, isn't it? Yeah? Everybody follow that? Now watch. Instead of that, I'm going to do the exact opposite. Instead of finding my center point, I'm going to let 1, 1 be my center point and find the equation that goes through it. It's going to be y minus 1 equals, what's my slope? 2 times x minus 1. And then I'm just going to simplify this expression. This is
2x
minus 2, and this is y minus 1, and I add 1 to both sides, and I get y equals
2x minus
Is it? Oh, okay. Got it? Try it with the red line this time. My red line has a slope of 4, and it goes to the point 2, 4. I think you're going to see that you're going to like it better. Write it out the way that opposite. What is it? Y
minus 4.
minus 4, that's going to give me my 4, equals 4 times,
X minus 2.
and then simplify. This is called the point-slope form of a standard linear equation. When you get into calculus, in Mrs. Kelly's class, she's going to expect you to do it this way every time. Because it's more formal and it's easier to understand your conic sections that way. And so we get y minus 4 equals,
4x minus 8.
and then you have to add 4 to both sides.
Y
And you
equals
get?
4x minus 4.
Y'all see what I mean about this one being easier? Try the black one up here. N equals 6, and you're going to the point 39. I want this line, I want the equation, so I have m equals 6, to 0.39. I'm talking about
Okay,
y minus 9 equals
6,
6 times,
x minus
distribute your 6, add 9 both sides, and what is y? 6x
3, y equals 6, x minus 9.
Those are the equations of my tangent lines. Guys all clear on that? Okay. Now what I'm going to do is I'm going to give you a sort of an application problem for derivatives. If I take a pen and throw it up in the air at 10 feet per second, and I'm going to throw it forward a little bit too, it's going to follow an arc. It's going to go up in the air, and then it's going to come back down again because of gravity. The function that we get from that is f of x, its position. We sometimes call it t of x for position. What is the effect of gravity? Negative 16x squared. I threw it upward at 10 feet per second. My velocity goes here, 10x. And it started about 4 feet off the ground when I threw it up in the air, so plus 4. If I look at this thing over time, just 1 second.
What was 10x again?
10 is the velocity that I threw the pen upward at. I threw it at 10 feet per second upward, and it's not going to take it very long to hit the ground. And it was 4 feet off the ground when I started, wasn't it?
Yeah.
What's going to happen is this thing is going to go up in the air a little bit, and then it's going to drop down, isn't it? What I may or may not be interested in, and I'm going to assume that I am interested in this, I am interested in the highest point that it comes to, its maximum height. Once you look at the tangent line, take a look at the tangent line as I start out. It starts out kind of steep, doesn't it?
Yep.
And then the tangent line tends to get smaller. The slope is getting smaller, isn't it? What happens at the very, very, very top of this curve?
Horizontal.
It's a straight line with a slope of 0, isn't it? Remember, this line, the slope of it represents velocity, doesn't it? You understand? This slope of this line represents velocity. Remember how we did it at the very, very beginning? It represents its... Doesn't it have positive velocity when it starts? It's going up? It has positive velocity. It's going in the upward direction. Then it slows down, doesn't it? As it gets closer to the top, doesn't it slow down? And for 1 instant, not very long, not like in the cartoons, but in real life, it pauses for that 1 instant at 0 velocity, and then it goes the other way, doesn't it? Because if it was positive, it started.
Like when you're in the car, you throw paper out, and then it stops, and it goes...
Well, that's something else, but you got the right idea. Okay, doesn't it stop?
I don't think so.
You understand that if I throw it straight up in the air, it stops and then it comes back down again. But there is that instant of time where it actually stops. That's going to be its maximum height, isn't it? You understand? That it's going to stop at its maximum height? In other words, its velocity is 0 at its maximum height. So if I find the derivative, f prime of x, go ahead and find the derivative. What do you do to get a derivative? Let's see. You take the exponent and you multiply it times the coefficient. The exponent times the coefficient gives me negative 32x to the 1, because I have to subtract 1, remember? Plus, what number's right here?
1,
1. I take the exponent times the coefficient.
10,
And x to the...
but you subtract when you get 0.
What is x to the 0?
Just one.
It's just 1, isn't it? Isn't anything to the 0 power 1?
So wouldn't it just be 10?
That's right, just 10. Exactly right. That's what I get. That's my derivative.
What about 4?
That's a good question. This has x squared, doesn't it?
Yeah.
And this one has x to the first. This one actually has an x number with it because it's a polynomial. It's x to the 0, isn't it? Take the 0 times the 4. 0 times the 4 gives you 0, and it's gone. Get it?
Oh, okay.
It's a really good question. It's a better question than you know. Okay, we got negative 32x plus 10 is our derivative. That means at any given point in time, my velocity is equal to negative 32x plus 10. What I might be interested in, for one reason or another, is its maximum height. Especially if I'm going to shoot off a rocket in the backyard, I might be interested in what its maximum height is. How high did it get? Well, I look at this, and when this is 0, I'm at my maximum height. Find this at 0. In other words, find the 0 of the derivative function. 0 equals negative 32x plus 10. Solve it. Go ahead.
10 over 32 equals x.
Yep. Which is reduced. 5 over 16, which is half of 5/8, which is 0.3125. Well, exactly that. Negative 32x equals negative 10. We subtract 10. We divide it by negative 32. Sorry. 32. We get x equals 5 over 16, which is exactly equal to 0.3125. Either one of these is appropriate. It's going to give me this x value, which is at 0.3125 seconds. But how do I find out how high it is? How high did it go?
Don't you plug it back in?
You substitute it back in, but you don't put it back in here, because that's going to give you 0, isn't it? You substitute it back in the original function, and it should give you your height above the ground. 0.3125 is my time. How high above the ground did it get? Substitute it in. If you want to, you can substitute 5/16, then you can do it in your head, but it's a little harder. Yeah, the calculator's a little easier. See, when you substitute in the 5/16, you get 25 over 256, but the 16 cancel out. And you get 25 over 16, negative. And this is 50 over 16, which gives you 25 over 16 plus 4, which is 5 and 5/16, 9/16, isn't it? Okay, take 5/16, square it, and you get 25 over 256. But you can forget about that because the 16, when you square the 16, you just end up with 25 over 16. It's negative. This is 50 over 16. Take negative 25 over 16, you get 25 over 16. That's 1 and 9/16. Add that to 4 and you get 5 and 9/16.
Isn't it 25 over 8?
No. Well, yeah, same thing, but we need 16ths because we're adding common denominators. Okay? 5 and 9/16. 5 point approximately 32? Or no, 5.2? What is it, guys? 5.625? Okay. 0.3125 seconds, and this is 5.6. What is this? Feet.
Oh.
And this is second. Isn't this our position?
Huh?
Its upward velocity or downward velocity is 0 at this point.
That's the highest point?
That's the highest point it's going to reach, 5.625 feet exactly. Now the really nice thing about this is we can get exact answers out. With our calculator, we can only get approximate answers. I think I have just enough time to go get the calculator and show you how to do it on there. Grab that. If you have one, go ahead and use it.
Wait, I think that these two, well,
What?
we multiply,
What you think?
when you multiply the equation here, they
No, that gives you 50 over 16. And that other one gives you negative 25 over 16.
very big.
Okay, here's my function, everybody. Negative 16x squared. If you put this in your calculator, make sure you use the negative key and not the minus key. Negative 16x squared plus 10x plus 4. Now what I need to do is if I want to look at it, if I look at it in standard, zoom 6, it gives me the full parabola, which is pretty steep, isn't it, with a negative 16 on it? It's pretty steep parabola. What I'd like to do is look at it more on the whole screen, like I did when I was graphing it before. So I need to change the, start with W. I need to change the window to 0, and it maybe goes to 3 seconds. And my Y minimum of 0, and maybe a Y maximum of 6. And then I can graph it, and it looks a little bit nicer. Now, this is the path it follows. What I'm interested in, and I'll get my crosshairs over there. I'm interested in the maximum point, right? Well, that's pretty close. Look, I get 0.32 and 5.5. Not bad. But I can also zoom in. Use your zoom feature, and you can zoom in on it, and you can get a little closer. See, I'm off a bit. There. Much better. 0.31 and 5.6. That's a little closer, and if I want to zoom in again, I just hit enter. I can get a little closer. I zoom in again, I can get a little closer. See, I'm off. There, a little closer there. One more time. I just keep hitting enter on the zoom feature. Now, I got 0.3124 and 5.562. Pretty close. That's 2 within 1,000. The thing I want you to keep in mind is that your calculator only calculates. It can't give you exact answers. When you're talking about astronomical distances, like when you send a probe up to Jupiter's moons, you're talking about 100 or 1,000 decimal places that you have to be accurate to. When you have to have that kind of accuracy, you have to find exact answers. Close isn't good enough. And for exact answers, you need calculus. The calculator's nice, and it's a nice tool, and it'll do some things for you. But when you need exact answers, you really need to know the calculus for it. Can you get any closer than that? No, yeah, you just keep hitting enter. You can get pretty close. The only thing that's going to be hard to tell where the middle is pretty soon. That's pretty close to the middle, and if I round it, I'm within 1/10,000th or so. Pretty close. All right, the point to this, the overall idea, is that if you take a function, any function at all, and I look at a function like this one, y equals x cubed minus 5x squared plus 4x minus 8, and I graph this thing, it's going to look something like, let's see if it goes over here, maybe comes down a little bit more and comes up. I think it looks something like this, more or less. Now what happens is we end up with, it's actually a little bit, it's not quite that, it's a little bit nicer curve than that one. But anyway, I want you to notice that I have 2 special points here. And if I look at the slope of the tangent line, what is the slope of the tangent line at this point? Isn't the slope of the tangent line 0 right here? And it's also 0 right here. These have names, they're called critical points. This one happens to be called a local maximum. Local because it's not the maximum point on my graph. My graph keeps going up forever. It just happens to be the close maximum, and this one's my local minimum. And if I want to find these, all I do is take the derivative derivative and set it equal to 0, and I can find the x values for both of those points. Then I can substitute those x's back in the original function and find the local maximum and the local minimum. This is what we use calculus for. A lot of times, a maximum or a minimum are of interest to us. Remember when we did the linear programming? Most functions don't follow a nice line. Most functions are curves. The only way to find a maximum or a minimum point on a curve is with calculus and finding the derivative and setting it equal to 0. Or at least it's a nice way of doing it. What is the derivative of this? Three x squared
Minus
minus
10x to the first.
10x to the first plus
4.
4. How many solutions does this have if it's equal to 0? Does it have 2 solutions? It's a quadratic, right? You can find the solutions using the quadratic formula. If you're lucky, you can find the solutions by factoring. I will make them factorable for you. The bad news, of course, is that you've got to have a leading coefficient, right? Yeah, this one's not factorable, but it could be. Let me see. No, no such luck. It is. X minus 2 and x minus 2. Is it factorable? No, not quite. Almost. Almost makes it. Not quite. We get a minus 8x in the middle. If I would have made this 2.5, then it would have worked out. But oh, okay. Good, yeah? You have a homework assignment you want to get started on. It's due on Monday, but you'll want to get a start on it tonight because you definitely have some questions. Look at the example, folks.
Watch it from the other camera.
Okay. What in the world? Hold on.
It's shocked me.
Oh. Well, you're in for it now, folks. You're in pre-cal. Sure enough. Yeah, I've done it too. You. I got your review already. Yeah, you did, definitely. I have it for you here. Yeah,
I'll be able to finish this.
what do you think, guys? Hard to understand? Easy to do, right? Is our homework going to be for you?
Hard to understand, hard to do.
No, it's not hard to do.
What do you do?
Monday.
I don't know.
What do you think, guys? Pretty fun? By the way, your first day in your calculus class, your instructor is not only going to go over this, they're going to start getting into the specifics of the H's and what happens when you do the limits and things, all in one day. Yeah, one day. Here you go. And they'll, of course, they won't speak English very well. It's going to be fun. Don't worry, you guys do it. That's the whole point. What's that?
The